Hey guys, Mr. L coming back at you with another video. And in this video, we're going to discuss periodic properties, and we're going to go a little bit more in depth on how the periodic table is structured. So let's get into this video. So the first thing we're going to do is just briefly review what we learned in a previous video about the periodic table. The first periodic table was constructed by a guy named Dmitry Mendeleev, and there was another chemist named Lothar Meyer, and both of them agreed, but Dmitry Mendeleev pretty much gets the credit for the periodic table development, that elements should be grouped based on similar chemical properties. And both of their periodic tables were based on increasing atomic mass as well as grouping of those different chemical properties of different elements. So based on this, there was a lot of spots missing since Dmitry Mendeleev came a while ago. They didn't have mass spectrometers and the ability to create new elements. So therefore, there was a lot of spots missing on his periodic table, but he knew that an element should be fitting there. And a good example of this is germanium, which he just called Ica-silica, or something that was below silicon. So he knew that there was an element below silicon, and there was properties that he predicted even though he didn't even see this or knew that it existed. So he called this element Ica-silica, and he thought the average atomic mass should be around 72 AMU, and with the mass spectrometer we found that it was 72.59 AMU. The next thing is he thought the density would be about 5.5 gram per milliliter, and it was determined to be 5.35 gram per milliliter. He thought it was going to be a high melting point for germanium, and we've later found that it was 947 degrees Celsius, which is very high. He thought it was going to be some gray metal, and we later found it was a very shiny gray-white metal. And then the last thing that he put there was that it was going to form a halogenated compound with 4 chlorine atoms to form that compound, and we later saw that germanium does indeed take 4 chloride ions to make a compound. So that brings us to our next guy that rearranged the periodic table, and his name was Henry Mosley. So after the Rutherford gold foil experiment and the determination that we have this small, densely packed, positively charged nucleus with some protons inside, and the number of protons is going to determine the element, Henry Mosley reorganized the periodic table based on increasing atomic number, and that's the periodic table that we have today. So this brings us to another piece of review. We have the idea of periodicity, or repeating pattern of elemental properties based on going through the periodic table. Directly after an inert noble gas, an unreactive noble gas, we have a very soft reactive metal, and these will repeat periodically, which we get the periodic function. So we've got a lot of different trends we're going to talk about in this video and the next video. It's going to be a 2-part series. We're going to talk about atomic size, ionization energy, electron affinity, electronegativity, different group properties, but we first need to talk about the most important property, and that's called the effective nuclear charge, because that's going to dictate all of the rest of the properties that we see on the periodic table. So our first trend that we're going to learn is called effective nuclear charge, and there's going to be 3 important pieces that we're going to need to know. We're going to need to know how many protons are in the nucleus. We're going to need to know if there are any core electrons, and then we need to figure out how many valence electrons we have. So there's 3 important pieces that we're going to need to figure out. So how we determine an effective nuclear charge is we need to use this equation, effective nuclear charge, which we symbolize with ZeEF, effective nuclear charge, is going to be the number of protons Z minus S, which is a screening constant, or the number of core electrons. So let's compare 2 elements from the second period. The first element we're going to look at is, say, carbon. Carbon has 6 protons in the nucleus, and our first complete orbital or shell that's been completed is the 1s. So we have 2 core electrons representative of helium's electron configuration. So we would take our 6 minus our 2, and carbon would have an effective nuclear charge of 4. If we were to compare that to, say, fluorine, fluorine has 9 protons in the nucleus. It has the same number of core electrons, 2, because it's got that complete helium shell before we go on to the 2s and the 2p. So therefore, we're subtracting 9 from 2, and its effective nuclear charge is 7. So as we go across the period, the effective nuclear charge is going to become greater and greater because you have more protons in the nucleus but the same screening constant. So what essentially a screening constant is it's a shield. It's got a shielding effect between the nucleus and the valence electron. You have electrons that are in the way, causing the nucleus not to be having a strong pull on the valence electron as opposed to if it was unshielded. The other direction on the periodic table that we're going to need to look at is going down a group. As we go down a group, you have more and more and more core electrons, so your screening value is going to be higher and higher and higher. Therefore, there's going to be less pull from the nucleus on those further away valence electrons with all that stuff, all that electron shielding in between. So as you go down the group, your effective nuclear charge is going to decrease. So now that we have a little bit better understanding of how we calculate an effective nuclear charge and the trend across the period and group, we have to think about the effective nuclear charge essentially as a vacuum. The stronger the effective nuclear charge, the more pull that we have on all of our electrons from the valence electrons, and they're going to be held more tightly. If we've got a lower effective nuclear charge, you don't have as much vacuum pull, so those electrons are going to be easier to be pushed out away from the nucleus. So that brings us to our next trend, which is atomic radius, or the size. So let's define what atomic radius is. We've got the van der Waals radius. The van der Waals radius is taking two atoms and smashing them together so you have a collision, and you're finding half the distance between the two closest nuclei can get from that collision. So you're taking the two atoms, you're smashing them together, and that point closest together that they get, you're going to take half the distance between the two nuclei, and that's going to be your van der Waals atomic radius. So let's start talking about the trend based on the periodic table. If we're thinking about the effective nuclear charge, remember the effective nuclear charge increases across a period. So we've got stronger and stronger pull, so therefore the atomic radius is going to get smaller and smaller as you go across the period because you have that stronger and stronger pull from the effective nuclear charge. If we're talking about going down a group, well, we've got more and more core electrons, so we have more and more shielding, as well as those electrons are going to repel each other, so they're going to get further and further away. We've got more electrons, more shielding, so as we go down a group, the atom's radius is going to get bigger and bigger. The other thing to mention here is that when we're talking about trends, you have to realize that this is just like any other trend, not talking about elements. So recently we had trends like UGG boots or hydro flasks, or wearing scrunchies. All of these things are trends, and not everyone follows the trend of liking hydro flask and UGG boots and scrunchies. So there may be trend breakers. So keep that in mind. Elements also follow trends, but there are some elements that may break the trend, so just keep that in mind. So let's discuss another thing that might affect our atomic radius, the idea of ionization. If we recall in previous videos, there are two different forms of ions that can form. We have cations, which are positively charged ions that are from losing electrons. And then we have anions, which are negatively charged ions caused by a gaining of electrons. So if we're talking about cations lost electrons, therefore the radius should be getting smaller compared to the parent atom. And the parent atom is just a neutral form of that specific element. If we've got a parent and it's got a certain number of protons in the nucleus, and the cation has lost electrons, but it's still got the same number of protons in the nucleus, therefore there's going to be a stronger pull on each remaining electron, causing them to get sucked in further compared to the parent. So there are two reasons why cations would be smaller than the parent. If we're talking about anions are gaining electrons. So there are more electrons being added, though it's got the same number of protons from the parent. So if we've got the same number of protons but more electrons, each individual pull on each electron from the nucleus is going to be less, as well as we've got electron pair repulsions. So those electrons are going to be clouded out, or the atomic radius is going to be getting bigger for an anion. So we have the idea of this isoelectronic series. And what an isoelectronic means, iso prefix means same. So something is going to have the same number of electrons. So if we had something like sulfide ion, chloride ion, potassium ion, and calcium ion, all of these would be isoelectronic with 18 electrons. The one that has to be the smallest is going to be the one that's lost electrons. So sulfide ion would be the biggest one because it's gained 2 electrons and it has the least number of protons in the nucleus. Calcium ion, the one that's lost electrons, would be smaller, as well as it's got the most protons in the nucleus. So when you're dealing with an isoelectronic series, typically the one with the most protons and the one that's lost electrons must be the smallest, and the ion that's gained electrons and has the least number of protons in the nucleus must be the biggest. So there it is, you guys. There's part 1 of atomic properties and atomic trends. If you enjoyed this video, if you found it useful, smash the like button, subscribe, send it to your stepbrother, send it to another sibling, send it to your favorite feline, and we'll see you in the next video.